Okay, we will be doing an experiment on freefall today, measuring the acceleration due to gravity. Have you discussed this in class already? I think it's chapter 3, objects in freefall. Okay, good. So I'll go over the experiment in a couple minutes, but first I want to introduce you to some terminology that you're probably familiar with, but maybe have never had explicitly defined for you. So I find that it often gets misused. And we're going to use this terminology in describing our experiments and their results, so it's important that we understand what they mean. Accuracy and precision. So we have a sense that we want our experiments to be accurate, we want them to be precise, but what exactly does that mean? So accuracy is how close your results are to what you expect, or to something you're comparing it to. It doesn't tell you about how repeatable the experiment is, or how good your results are, just how close they are to what you expect. Whereas precision is how repeatable the experiment is, which in a sense is a measure of how carefully you've performed the experiment. So accuracy we usually express as a percent error. So today we're going to be measuring the acceleration due to gravity. Our textbook tells us that's 9.8 meters per second squared. So if we measure 9.9 meters per second squared, we can express that difference as a percent error. How much is the difference compared to the measurement that we expect? Okay, and that's something we're going to frequently do, particularly when we have an expected value. Precision is really measured by our uncertainty. If we have an uncertainty of plus or minus 0.1 meters per second squared, that is our precision. And it tells us if we repeat the measurement, how close we expect to get to the measurement we got the last time. Now, it could be that every time we do the experiment, we're getting something different than what we expect, but as long as we're consistently getting the same different value, we can say our measurement is precise. Okay, so an analogy here, you can think of like an archery target, a bullseye, or a dartboard. If I shoot 3 arrows at this, and I am both accurate and precise as an archer, where do I expect those 3 arrows to go? Yeah, in the middle. I expect them to be clustered around a tight circle and in the center. But what if I'm accurate, but I'm not precise? What would that mean in terms of where my 3 arrows would go? So they're going to go around, and sort of their average value is going to be centered on the target, but they're going to have a lot of scatter to them. Okay, so my shots aren't very repeatable, but on average, they're going in the right place. So that is something that's accurate, but is not precise. What would it look like if something was precise, but not accurate? Okay, so they're clustered together very tightly, but not at the center. And then finally, what if they're not accurate or precise? Well, they're scattered all over, and the sort of average position is not at the center of the target. All right, so when you see something like this, that's in a measurement, where your measured values are scattered around your expected value, that means you're relatively accurate. I mean, you'd like to be accurate and precise. If you're precise but not accurate, if you're measuring something repeatably, but it's not what you expect, that usually means there's some systematic error. There's something you're not accounting for in your measurement. In the example of shooting an arrow at a target, what might we not be accounting for in this example here? We're very consistent, but we keep missing by basically the same amount. What might account for that?
The resistance of the air.
Okay, maybe, and specifically wind might blow them off to one side. Right? And if I haven't accounted for that when I aim the arrow, right, that's going to show up. That's what we call a systematic error. Whereas something like this, where I'm just sort of scattered all over, that's probably limited by my ability. Right? And so that's what we call a random error. Okay, so we use these terms precise and accuracy, and we'll quantify them by percent difference for the accuracy and uncertainty for the precision. Okay, so with that in mind, our experiment today is to measure the acceleration due to gravity as an object falls freely. At least that's the assumption, that our object will fall freely. So our object is just going to be a mass. So you have these mass kits in front of you with a variety of masses. You will be asked to use one particular mass, and then your partner will be asked to use a different mass. So I suggest a mass of 500 grams to start with. And then when it's your partner's turn, and they're going to use a different gram, you can just hook another 200 grams on the bottom, do 700 grams. It's sort of the easiest way to go. And what we want to do is measure how fast these fall when we drop them, or more precisely, what their acceleration is. So to do that, we have a couple tools at our disposal. We have these tape timers. So these are mounted on a base that is sitting on your table. What we're going to want to do is put the base at the edge of the table and pivot this around so the tape timer is reaching out over the edge of the table, okay, like this. And since today is the first lab of the week, yours may not be positioned like this yet. You want them leaning out over the table. And then we have ticker tape in a long spool. It should be in front of you. You want to tear off just enough so that the bottom of the ticker tape is at the floor when the top of the ticker tape is at the height of your tape timer. And then what we will do is thread this through the guides in the timer. And when we do, the tape will be between this little strike plate on the outside and a piece of carbon paper on the inside. So inside this box, there is a timer that has a little hammer that will pound 40 times per second. And when it pounds, it will hit the carbon paper, push that into the strike plate, and leave a dot on the paper. So we'll use that to time, or to keep track of how far the tape has fallen as a function of time. And the reason the tape is going to be falling is because we're going to tape it onto our mass. So you can do that however is most convenient and easy for you, usually looping the tape around the hook. Works pretty well. Okay, so the idea is that we're going to drop this with the timer on. It will make ticks every 40th of a second. And when we're done, we'll have a bunch of dots on our paper that look like this. A couple things to be careful of. You don't want to drop it just like this, because if I do, as the mass falls, the tape has to whip around, and that's going to produce friction. And we're trying to measure an object in free fall. Free fall is when only gravity acts on an object. So we're assuming there's no friction. So it's much better to hold the tape vertically and drop it like this. So the timer is battery powered. There's a switch, and it can turn in two different directions. This one, this direction, is labeled 10 hertz. That means 10 times per second. And listen to what it sounds like. That is not what we want to use. We want to use the other direction. Hear the difference? So that's ticking 40 times per second. It will give us more data points to measure. Okay, so we turn it on 40 hertz. We hold the tape straight. And we drop. Did anybody notice anything about the mass on its way down? It clonked on the side of the table. Okay, so was my object in free fall as it was going down? No. Okay, so I would want to throw away this tape and start over. Okay. One thing you may find is that if you're having trouble getting it to not clonk the side of the table, if you do it 2 or 3 times and it keeps happening, rather than using a really big mass like this, use a much smaller one, physically smaller, thinner, and to get the same amount of mass, you can just hang a bunch of masses off the end, and that is less likely to crash into the side of the table. Okay, so our ticker tape should look something like this when we're done. There's a few things to note. There will be a cluster of dots at one end. What did that come from? Yeah, that was when I held it still and turned on the timer. The tape wasn't moving, but it was making marks. Okay, so I don't want to use those. The object was not in free fall there. I was holding it. So I want to go to the first dot that's well spaced from that cluster. And I'll call that dot number 1. And by well spaced, something like a centimeter or so will ensure that it was actually falling at that point and not just due to your hand moving up and down a little bit before you let go. And then I want to go through and I'll circle each dot because they're typically quite faint. And so it's useful to just spend a minute locating and identifying them so that you can come back to them later. And I can kind of see a pattern. Each dot should be getting a little further than the one before it. But there's something that disrupts this pattern. So the spacing gets a little bigger, a lot bigger, and then shorter. Something funny is going on here. Can you imagine what might cause something like this? Yeah. Well, if it hits the table, you'll know it hit the table. You should throw away your tape before even getting to this point. What probably caused this is sometimes that hammer hits the carbon paper and it doesn't make a very good mark. So you may not be able to see every dot. So I suspect that there was supposed to be a dot there and it just didn't show up. Okay, so you will probably have one or two of those. If you have more than that, it may mean you need new carbon paper. I have carbon paper up here somewhere. So if you need new carbon paper, if your dots aren't dark enough, come up and see me and I'll get you set up with that. But I want to identify where there may be missing dots. And then when I number my dots, I can't record any values for that, but I can note that it's missed by skipping the number. And call this my first, second, my fourth, fifth, and sixth dot. And I just won't have a third data point. Okay, then in the corner of the room, we have meter sticks. We have 2 meter sticks as well. So, we get a shorter one for the purposes of showing you on the board. You will measure distances from your first dot to each of the successive dots. I'm sorry? I'm not going to measure the missing one because I don't know where it is. So I'll measure these distances. Okay, and I'll call them, this distance I'll call y2. This distance here I'll call y4. This distance here I'll call y5. And this one I'll call y6. I have no y3 because I have no dot. Okay, so I'm missing a dot. I just won't record that. And then I can graph these. And when I graph them, I should get something that looks like this. I expect the motion to be parabolic, okay, because my equation for an object in free fall is quadratic. Right? It's got this quadratic term. If it starts from rest at position 0, then I get this nice parabola. Now, my data won't exactly fit on a quadratic curve. If I look at these points and I try to draw a quadratic curve through this, I might get something like that. Okay, and I can use a number of different software tools to draw these curves through my data. We're going to use one called Logger Pro today. Logger Pro is on all these lab computers. It's also possible to download it onto your laptop. So there's a link in your lab manual for where to go to get that. We have a site license to it, so it's not freely available, but we have a password that you can use. Yes?
So I tried to download it, but then it said that I don't have permission or something. So.
Okay, yeah, so if you have a laptop, you want to do it on your laptop, maybe at some point today you can come up and I can help you with the download if you're having trouble with it. Okay, so we will type in the values for the time into one column. Every 40th of a second, we're getting a tick mark. So T1 is going to be 0.025. Right, that's 1/40th of a second. The next point is going to be 0.05. And likewise, we'll fill out the columns, or the cells for the time. And for the height, we'll plug in our measurement values. And Logger Pro will generate this plot of the data points, the blue dots, and then we'll tell it we want to do a curve fit. So what a curve fit is it where you tell the computer there should be some functional form to your data. And we're going to use this quadratic form here. And it will try to vary these parameters, A, B, and C. These are called the free parameters. So that for every value x on my curve, when it calculates this function, it gets a value y that's close to my data. And so basically, it will try different values of A, B, and C to draw a quadratic curve. It will ask how close is that curve to my data, and then it will try different values of A, B, and C to see if it gets a better fit. And it will do this many times until it gets the best fit. It's called a best fit line or best fit curve. Okay, so how does it know how good a fit it is? We measure how good the fit is by keeping track of how far the average point is from the curve. Right? So some points will be above the curve, some points will be below. We don't expect all the points to fit on a curve. Exactly, why not? If this red curve represents an object in free fall with an acceleration of g, why are my data points not going to lie exactly on that curve?
Because it's
Because there's uncertainty. I have experimental uncertainty. Because of that, I don't expect my data to be exact. Some of it will be a bit high, some of it will be a bit low. And so the distance from the data point to the line we'll call delta, the error of that data point. And so we have delta 1, delta 2, delta 3 is the errors of the first three data points. Then the quantity that tells us how well this curve fits to our data is called the root mean square error. And I get that by adding up all of my errors. So if I have n data points, I add up the error for all n data points. The problem is, if I just add up the errors and take some sort of average, if some values are a little bit high and some values are a little bit low, some errors are going to be positive, some are going to be negative. Okay, so if some of my data points are above my calculation and some are below, then when I add them up, they're going to cancel. So what I want to do is I want to square the error first so that regardless of whether the point is high or low, it gives me a positive error. And then I'll average those squares, and then I'll take the root of that to get a quantity that tells me how far the average data point is away from my curve. We call that the root mean square error. Okay, the units on this are going to be whatever the units were on my y-axis, because it's measuring a distance vertically on the graph from an average data point to the height of the curve that goes by it. Okay, so the smaller this is, the better the curve fits the data. So you can kind of imagine what the computer is doing. It's picking values for A, B, and C. It's calculating the height of this curve at the time where I recorded each data point. It's measuring all the errors, and from those determining the root mean square error. And then it tries different values of A, B, and C and sees if it gets a smaller value. OK, so what I'm going to want you to do is after you've entered all your data, tell the computer you want to do a curve fit. The lab manual explains the process. You go to, I think, the Analyze menu, Curve Fit. It will ask you for the form that you want. It's got linear, proportional, quadratic. Choose the quadratic one of this form. And then it will ask you what values you want to use for A, B, and C. So the first thing I'd like you to do is plug in what you expect A, B, and C to be. OK, so for instance, if this quadratic function represents this equation of motion, what is capital A in terms of the parameters up here? It's the coefficient in front of the squared term. It's 1/2 times the acceleration. And so what would I expect that to be numerically for an object in freefall? Well, AY is 9.8 meters per second squared. So I'd expect this to be about 4.9 meters per second squared. Okay, and if I've measured all my heights in centimeters, then this would be, I'd plug in 490 centimeters per second squared. If I've measured my heights in millimeters, I'd convert this to millimeters per second squared, 4,900. All right, what about B? If I release my object from rest, what should B be? It's the initial velocity, right? And so if I release it from rest, that's going to be 0. And then C is the starting height. And I started my measurement from a height that I called that first position 0. So I expect that to be 0. Okay, so I can plug in these numbers. These are my estimates for what they should be into the computer, and it will draw a line. I should say it will draw a curve. Okay? The curve will not go through my data very well. Okay, because these expected values are not actually the ones that I measured. My measurement's going to be off from that a little bit. And in particular, if I assume that I dropped it from rest, I mean, that's reasonable. I did. I released it from rest. But if I think a little more carefully about what this is, the initial velocity is the velocity at time 0. But my first data point is not time 0. It's time 0.025. Right, so the actual initial velocity is just before that. The actual first position is not 0. It's where it was at time 0. Okay, so these values that I plug in are close, but they're not exact to what my measurement represented. So then I will ask the computer to see if it can find a better fit. Okay, so when I do this, I'll get a little box over here, and it will say A equals, B equals, C equals, and then it'll say RSE equals, and then some number. RSE is what the computer is calling this. We call it the root mean square error. The computer is calling it the root square error. Record that number. And then note what happens when you tell the computer to try to find a better fit. It will think for a minute or so, actually for less than a second, and then it will draw a line that's a much better fit, and it will plot the parameters of that fit. Or it will state the parameters of that fit. And what you'll find is the root mean square error for the computer fit will be better than the one you found. It will always be better. Or at least it cannot be worse, because the computer is going to keep searching until it finds the smallest error, right, where you just tried one value. It will also give you an estimate for the uncertainty in these quantities. Right? If your data is scattered, then there's some range of values that can draw curves that reasonably fit the data. So it will tell you the uncertainty here. So we can use that as an estimate for how well we know the acceleration due to gravity. Okay, so it will tell us a value for A, B, and C. The value we get for A, we can use to find the acceleration. And since the object's in free fall, we can call that G, the acceleration due to gravity. So we will get a measure of G that has uncertainty. If I get a measure of G that says G equals 974.3 plus or minus 7.2 centimeters per second squared. Does this agree with the accepted value of 9.8 meters per second squared? So first of all, what is 9.8 meters per second squared in centimeters per second squared? 980. Okay, so we're going to compare this to the accepted value of 980. So how do I know whether this agrees or not? Okay, so I could say the difference between these two is about 6 centimeters per second squared, which is less than the uncertainty. I could say it differs by about 6 over 7.2 uncertainties. So basically, this is a range. If I think of it as a range, it goes from 967 to 983, and that includes 980. So if the accepted value for G is within the range that you measure, you can state that you were able to measure the expected value of the acceleration due to gravity within your measurement uncertainty. Okay, if your values do not encompass this, let's say you measured the exact same value, but your uncertainty was smaller. Let's say it was an uncertainty of 1.2 centimeters per second squared. Now, the accepted value does not fall within that range. So all you can say is that you did not measure the expected value, that you were off. Your measurement was off by a certain percent. Right? That's where accuracy comes into play. You can talk about the accuracy. And you can hypothesize why not. If the measurement is a little bit low, it could be that there was some friction, some air resistance, something like that. You might even be able to test your hypothesis. You might be able to go back with a larger mass, for instance, and see if that makes the effect of friction or air resistance more negligible. Okay? So that's sort of the procedure you want to use when you get unexpected results or results that don't agree. You want to hypothesize what could have gone wrong, see if you can verify that with experiment.